Okay, get this. Computers that run on quantum mechanics, like all that weirdness of the quantum world.
Right.
It's almost science fiction-y, but it's not.
Not at all, yeah.
This is actually happening right now. You might have heard about quantum computers like it's some far-off thing.
Mm-hmm.
But this is about a bridge being built right now, like
It
today.
is, yeah.
So we're doing a deep dive on an essay. It's by Jorgo Schneeppot.
Okay.
The title, if you could even believe this, it's in German, Quanten Hybrid Computer. Vereinigung von Quanten und Klassik,
Okay.
which, for everyone listening, means quantum hybrid computers. Unification of quantum and classical.
That's it.
Schneeppot, in this essay, he doesn't just tell us what hybrid computers are. He really gets into why they're such a big deal.
Yeah, he really lays it out.
Like, I was surprised reading this. It's not just some lab experiment. This is relevant stuff.
Yeah, he starts off Schneppe by talking about this problem that's been bugging computer scientists forever, like our normal computers.
Right. The ones we use every day.
Exactly. They hit a wall with certain kinds of problems.
It's not just that they're slow, right? It's like the type of problem.
Yeah, exactly. It's the nature of the problem itself.
Schneeppot, he uses this example, the traveling salesman problem, where you got to find the shortest route.
Right, through all these different cities.
Yeah, seems simple, but as you get more cities, like, the possibilities just explode.
They just, yeah, overwhelm even the most powerful computer.
Like planning a road trip with 100 stops, your computer's just like, nope.
Pretty much, yeah.
And this isn't some, like, theoretical puzzle, right?
Yeah.
These NP-hard problems, they're everywhere.
Oh, they're everywhere. Think about traffic in a big city, or global supply chains, or how molecules interact, that stuff.
Like for drug development?
Exactly. Those are huge real-world things, and our computers, they just choke.
Which is where quantum computers come in, right? Like the idea of superposition, entanglement.
Right, massive parallel processing.
It's like the ultimate cheat code for computing.
Mm-hmm.
But Schneeppot, he's not all quantum hype, is he?
No, he's very grounded. He sees the potential, definitely, but also the huge challenges.
What?
Well, like decoherence, where the quantum state, it's so fragile, it gets messed up easily.
Leading to errors.
Yeah, and then you need thousands of qubits, these stable ones. We barely have hundreds.
And don't forget the energy to keep them near absolute zero.
Oh, yeah. Cryogenic cooling is a whole other beast.
It makes you wonder, are we waiting for this perfect quantum computer that might never come?
And that's where Schneeppot's argument for hybrid computing comes in.
Yeah, what's his take?
He says, let each computer do what it's good at. Classical computers, they're great for handling data, control flow, analyzing results.
Okay.
Quantum computers, they tackle that specific hard part of the problem.
So it's not about replacing, it's like a dream team, each player with their own strengths.
Exactly.
This blew me away. This isn't just an idea. Schneeppot talks about hybrid systems that are already out there.
Oh, yeah, they're doing amazing things.
Like IBM, they have this cloud platform where researchers can access their quantum computers.
Mm-hmm. Superconducting qubits.
It's wild, but there are different approaches, right? It's not one size fits all.
Right, and Schneeppot talks about that. He talks about D-Wave.
Okay.
They do this thing called quantum annealing.
Interesting.
It's good for certain types of optimization problems, like finding the lowest point in a really complex landscape.
I'm picturing a skier trying to find the bottom of a valley.
Yeah, like that.
Okay, so we're seeing all these different approaches, each tackling a different piece,
Mm-hmm.
which leads to the big question, what can these hybrids actually do?
Right, what problems can they solve that regular computers can't even touch?
That's what I want to know.
Yeah, and Schneeppot gives some really cool examples. Let's start with that traffic flow problem.
Okay, yep.
Imagine using a hybrid computer to analyze all that real-time traffic data and adjust the lights on the fly.
To minimize congestion.
Yeah, and travel times.
Wow, that's super practical.
Right. And he's not just theorizing, he points to research where it's actually happening.
That's awesome. Okay, so traffic, what else?
Well, think about supply chains, those global ones, super complex.
Yeah.
Hybrids could optimize those, how things are made, shipped, delivered, the whole thing.
That would be a game changer, especially now with how global everything is.
Absolutely. And it's not just about speed or cost, it's about making them more resilient, more sustainable.
Less waste, less impact on the environment.
Exactly. It's about solutions that are good for business and the planet.
Okay, I'm sold on the optimization front. But what about other areas? Schneeppot talks about materials science.
Right?
Like designing new materials at the atomic level. That's just mind-blowing.
It is. Think about it. You can simulate and test new materials virtually.
No more expensive, time-consuming lab experiments.
Exactly. And you can explore so many possibilities, tweak the properties atom by atom.
To create materials with, like, crazy strength or conductivity or heat resistance.
It's not just discovering new materials, it's designing them for a specific purpose.
Schneppat uses the example of batteries, like designing better batteries.
Mm-hmm. Simulating different chemistries, optimizing for performance, safety, environmental impact, all of it.
Now, that's a future I can get behind, but
Yeah.
let's be real for a sec. Schneppat loves this stuff, but even he admits there are some big challenges ahead.
Oh, definitely. And understanding those is crucial if we want to really grasp this whole field.
So what are those hurdles, the things that are still holding us back?
Well, let's dig into those in the next part of our deep dive. It's going to get really interesting.
All right, sounds good. We'll be right back.
Welcome back. So before we go full on sci-fi future with hybrid computers, we got to talk about the roadblocks, the things that are slowing us down.
Yeah, it's easy to get carried away with all the possibilities, right?
Totally. And Schnippat gets this. He doesn't shy away from the challenges. He says facing them head on is how we innovate.
Makes sense. So what's the biggest hurdle?
Scalability, it comes up again and again. It's,
Okay.
it's not just about cramming more qubits into a system.
Right, it's got to work.
Yeah, you need stability, coherence, they got to work together.
It's like a giant house of cards. The bigger it gets, the more likely it is to collapse.
That's a good analogy. And this instability, we call it decoherence in the quantum world.
Right.
That's the Achilles heel. It's the loss of that delicate quantum state.
The thing that makes it so powerful.
Exactly. It's caused by any interaction with the outside world, vibrations, temperature changes, stray fields, anything.
So how do you stop that? Can you even shield these qubits completely?
It's a huge challenge, no easy answers. Schneppat talks about a bunch of approaches.
Like what?
Well, one is physical shielding, like literally building environments to isolate the qubits.
Wow.
Think super precise temperature control, vibration isolation like you wouldn't believe, magnetic shielding that blocks out even the Earth's field.
It's like a quantum sanctuary where these qubits can just do their thing undisturbed.
Kind of, but Schneppat also points out it's not just external noise.
Right, there's got to be stuff going on inside the system, too.
Exactly, and that's where error correction comes in. This is fascinating stuff. Basically, you use redundant qubits, multiples, to represent one piece of information.
So if one messes up, the others can fix it.
Exactly. It's like a backup system built into the quantum computer.
That's smart, but it sounds complicated.
Oh, it is. Computationally expensive, needs even more qubits, more connections, more chances for something to go wrong.
But this is where the hybrid approach shines, right?
Exactly. Think about it. We've got decades of experience with error correction in classical computers.
Yeah.
With hybrids, we can use that knowledge to make the quantum side better.
So it's like a quality control team checking the work of a genius but messy artist.
That's a good way to put it. And it's not just error correction. Schneppat talks about algorithms.
Wow.
You need special algorithms to bridge the classical and quantum worlds, translate problems, interpret results.
It's the whole new language of computing.
Yeah, and Schneppat calls it an interdisciplinary problem. You need physicists, computer scientists, mathematicians all working together.
Okay, so we've got decoherence, error correction, algorithms, but what about actually building these things?
Right. The hardware itself is super complex, special manufacturing materials, and then there's the cooling.
Keeping it near absolute zero, that can't be easy.
It's not, and it's expensive. Schneppat says the cost is a huge barrier right now.
Especially for smaller research groups.
Yeah, cryogenic cooling alone, that's a ton of energy. Special equipment, it adds up.
So no quantum computer in my basement anytime soon.
Probably not, but Schneppat says this is normal for new tech. As things improve, costs come down.
Okay, that makes sense. Mass production, all that.
Exactly, and he mentions another possibility, new types of qubits.
Oh.
Some researchers are working on qubits that don't need such extreme cooling.
So maybe less energy, less complexity.
Potentially it's early days, but it's an exciting area.
So it's not just about making what we have cheaper, it's about finding new ways.
Exactly. The point is, even with all these challenges, the potential is so huge.
Yeah.
People are really pushing to make this happen.
It's inspiring. It feels like we're at a turning point in computing.
I think so too. And it's not just about faster calculations or better algorithms.
It's bigger than that.
Yeah, it's about tools that could change how we understand the world, how we solve the big problems.
Like climate change, healthcare, all that.
Exactly. And that's what we'll talk about in the next part, the real world impact of this tech.
Okay, I'm ready. Let's do it.
Yeah.
Welcome back. So far we've talked about what hybrid computing is, why it's such a big deal, even some of the hurdles. But honestly, what gets me excited is, like, the so what?
Yeah.
What can this actually do out there in the world?
Yeah.
Schneepat, he gives some pretty amazing example.
Oh, he does. He really paints this picture of a future where these computers aren't just for scientists, you know?
Right.
They're part of everything: healthcare, manufacturing, finance, even how we understand the universe.
That's a lot to take in. Maybe we start with something specific, like Schneepat talks about drug discovery.
Okay.
That's ripe for disruption, right? How does that look different with hybrid computers?
Imagine developing new drugs, therapies, and it doesn't take years, billions of dollars.
Right.
Schneepat says hybrids could speed that up massively.
Well, how so?
Well, instead of mixing chemicals, testing stuff in a lab, you simulate it.
At the quantum level.
Exactly. It's like a virtual lab. You test millions of possibilities without even touching a beaker.
That's wild, so it's faster.
Way faster, but also, Schneepat points out, you get insights you couldn't get in a normal lab.
Like what?
Like how molecules really interact at that level. You could design drugs that are super precise, target specific things.
Fewer side effects, better results.
Exactly. It's like a molecular scalpel instead of a hammer.
And it's not just drugs, right? Schneepat talks about material science, too.
Oh, yeah. Imagine designing materials atom by atom to have the exact properties you want.
So like superconductors that work at room temperature.
Right. Revolutionize energy transmission. Or materials that are crazy strong but super light.
For airplanes, buildings, all that.
Exactly. Schneepat even talks about better solar panels, ones that capture way more sunlight.
Making renewable energy even better.
It's like a materials revolution, and hybrids are leading the way.
This is getting me excited, but Schneepat's vision goes even further, right?
Oh, yeah, he talks about finance, optimizing models, making markets more efficient, less likely to crash,
And climate models, making them more accurate.
so we can better understand and deal with climate change. It's huge.
It's almost like this technology could solve all our problems. But, gotta ask, is Schneepat being too optimistic?
It's a good question. And he does say any powerful tech can be misused.
Right.
But he argues the potential benefits, especially for health, climate, those are too big to ignore.
So it's a balancing act, risks versus rewards.
Exactly. And that's why it's so important to talk about this stuff openly, you know?
Not just scientists, but everyone.
Yeah, we got to have conversations about the ethics of this, make sure it's developed responsibly.
They benefit everyone, not just a few.
That's the goal. And that's why shows like this are so important, making these complex topics understandable.
Starting the conversation.
Exactly. Understanding the potential, the challenges, the ethics, so people can make informed decisions.
Well said. This has been a fascinating deep dive, I gotta say. I'm really excited to see what happens next.
Me too. It's a field with so much potential. We'll definitely be revisiting this, I'm sure.
Thanks for joining us on this deep dive. Until next time, keep exploring, keep learning, and keep asking those big questions. That's how we move forward.